All right, let's get right into it. At the very core of all science, I mean all of it, is one simple act: measurement. It's how we take the messy, chaotic world around us and turn it into numbers we can actually work with. But here's the thing you might not realize. There's a whole hidden set of rules that governs every single measurement we take. And if you understand those rules, well, you're on your way to understanding how science really works.
I mean, think about it. We've all been there, right? Maybe you were trying to bake something and you put in a tablespoon of salt instead of a teaspoon. Disaster. Or you're putting together some IKEA furniture and you use a screw that's just a millimeter too short and the whole thing is wobbly. A tiny mistake can just completely derail everything.
But imagine scaling that up. When you go from your kitchen to a physics lab or a massive engineering project, the stakes are just way, way higher. A tiny error isn't just a bummer. It can be the difference between a breakthrough discovery and a catastrophic failure. Precision isn't just a nice to have, it's absolutely everything. To really get why these rules are so critical, you have to picture what science was like before them. And honestly, it was pure chaos. It was like trying to build a skyscraper with a team where everyone is using a different-sized ruler and speaking a completely different language. It just wouldn't work. For the longest time, different groups of scientists had their own systems. So you've got the CGS system using centimeters and grams. Over here, you've got the British FPS system with feet and pounds. And then there's the MKS system with meters and kilograms. A scientist in one country could be doing an experiment that was basically impossible for someone in another country to replicate accurately. It was an absolute recipe for confusion.
So yeah, the global scientific community realized, okay, we've got to get on the same page. They needed a single, universal language that everyone could use for measurement.
And the solution that came out of this was the System International Day Unites, or as pretty much everyone calls it, the SI system. And this wasn't just another system to add to the pile. This was a global agreement to create one single standard, to bring some much-needed order to the world of science.
This whole system is built on just 7 fundamental pillars, these 7 base quantities you see here. You can think of them as the alphabet of science. Literally everything else we measure, from the velocity of a rocket to the brightness of a star, is just a combination of these 7 basic units. Now look, if you go look up the official definitions for, say, a kilogram or a second, they are wild. They're based on things like the speed of light and the Planck constant. But you don't need to memorize any of that. The big idea, the really important takeaway is this. Our measurements are no longer tied to some physical object sitting in a vault somewhere. They are based on the unchanging, fundamental laws of the universe itself. That makes them incredibly stable and truly universal.
So, we've got our universal language. Problem solved, right? Well, not quite. Turns out there's a much more subtle problem that every single scientist has to deal with, and it's baked into the very act of measuring something.
Because here's the secret. No matter how fancy your tools are, no measurement is ever perfect. Ever. Every time you measure something, you're getting an approximation. There is always some degree of uncertainty. So the question for science became, how do we communicate just how good our approximation is? And that brings us to the hero of our story, significant figures, or sig figs, as you'll often hear. This is the clever system scientists use to be honest about their precision. A sig fig includes all the digits in a measurement that you know for sure, plus one, and only one, final digit that's an estimate. Let's take an example. Say you time something with a stopwatch, and you get 1.62 seconds. What you're really saying is that you know for sure it's 1.6 something. That 1 and that 6, those are certain. But that last digit, the 2, that's your best guess, based on where the needle stopped. It's uncertain. So this measurement has 3 significant figures. Okay, so how does this actually work in practice? Well, it all boils down to a few simple rules that let scientists communicate how precise they're being without having to write a whole paragraph about it. So here are the key rules. First off, any number that isn't 0 is always significant. Easy enough. Second, any zeros that are sandwiched between non-zero numbers, they count too. Third, leading zeros, the ones at the very front, they never ever count. They're just there to hold the decimal place. And then you've got the tricky one. Zeros at the end of a number only count if there is a decimal point somewhere in that number. It's a huge difference.
But this is where it gets really important when you start doing math. When you multiply or divide measurements, your final answer can't be more precise than your least precise number. So, you round your answer to the same number of significant figures as the input with the fewest sig figs. But, and this is what trips people up, when you add or subtract, the rule is different. You round to the lowest number of decimal places.
Okay, check this out. We're calculating density, so we're dividing mass by volume. Our mass measurement has 4 sig figs, but our volume measurement only has 3. So even if our calculator gives us a number like 1.688048, we can't report that. We have to be honest. Our weakest link only had 3 sig figs, so our final answer can only have 3. We rounded it to 1.69.
So far, this might seem like a bunch of annoying, tedious rules, but I promise you it's not just about bookkeeping. This is about unlocking a much deeper, more powerful way of thinking about the world. And that power is something called dimensional analysis. Seriously, this is like a physicist's superpower. It's a way to check if an equation in physics even makes sense in the first place, before you even think about plugging in a single number. Think of it like a grammar check for the universe.
The whole idea is actually pretty simple. You can break down any physical measurement into its most basic dimensions: mass, which we call m, length, L, and time, t. And here's the rule. In any real, valid physics equation, the dimensions on one side of the equal sign have to be exactly the same as the dimensions on the other side. You can't have an equation that says a length equals a mass. It's just nonsense.
So let's put this to the test. Let's say you're in an exam and you can't remember the exact formula for kinetic energy, K. You remember it involves mass, m, and velocity, v, but you're just not sure how they're combined.
Okay, so maybe these are the 3 formulas you're considering. Now, without dimensional analysis, you just have to guess or go look it up. But with this tool, we can actually rule out the impossible ones right now.
All right, let's do the check. We know that the dimension of energy is mass times length squared divided by time squared. That's our target. So let's look at the first formula. When we work out its dimensions, nope, not even close. It's out. What about the third one? Well, that gives us the dimensions for force, not energy, so that one's wrong too. But wait a minute, look at the middle one. The 1/2 is just a number, it has no dimensions, and when you work out the dimensions for m times v squared, bingo, it's a perfect match. It's the only one that could possibly be right.
And that right there, that is the superpower. Now, this method doesn't prove an equation is 100% correct. Notice it couldn't tell us about that 1/2. But if an equation is dimensionally inconsistent, it is guaranteed to be wrong. It's a physicist's first and best defense against making a mistake. It's pretty amazing, right? This whole journey started with something as simple as agreeing on how to measure things. But it leads us to this profound idea that the universe has a deep, logical structure, a kind of grammar, that we can actually check. And it just makes you wonder, if we can see the logic hidden inside our formulas like this, what other incredible, hidden structures are just out there, waiting for us to find the right way to look?